Welcome to Radar in Action at Fraunhofer FHR in Bachberg, Germany. My name is Jens Wiege and I'm glad that you are with us again. As you can see, today is another special edition. We are broadcasting live from our largest experimental system, the Space Observation Radar TIRA. I am inside the TIRA Dome on the second floor, on the balustrade, balcony or walkway or whatever else it's called here. The TIRA Dome protects not only the antenna and the whole high-frequency technology from wind and weather, but also me. Because outside it is really usselig, as we say here in Rhineland near Cologne, too cold drizzle. Let's take a look around. Behind you can see the concrete base of the large antenna. Okay, base actually sounds too shallow in this case, because this one is estimated to be 15 or 20 meters high already. And if you look to the left, you will see my colleague Dr. Vassilis Karamanavis from the Department Radar for Space Observation on the first floor on the balustrade. He will now look up with you at the antenna and into our control room. Then we'll get into our topic for today, observing and supporting deorbiting operations with the TIRA Space Observation Radar. Then I'll turn over to Vassilis now. Let's go.
Thank you so very much for your introduction, Jens. So, welcome under the TIRA Dome. What you see behind me is a nice view from the back of the antenna. You see basically the 34-meter diameter antenna along with a concrete pedestal that the antenna sits on. This is actually a very dynamic system because our antenna is a record holder when it comes to rotation around the azimuth. More about this later during the actual presentation. We can move the antenna with about 26 degrees per second, and in fact this is a record holder. In fact, when one sits where I'm sitting here, when the antenna rotates at its maximum velocity, one can feel the wind from it. Meet me in the TIRA control room. So, welcome to the TIRA control room. This is the place. This is the place where all critical functions and everything is controlled during observation. Here we have the seats for two operators. On the upper panel right here, you can see a number of screens which give us live feed from the antenna, its motion during the observation, as well as other critical components of the system, for example, the microwave amplifiers. On the left part of the main panel sits the lead operator, which takes care of the observation from start to finish, and is responsible for the general health of the system and the observation to go well. Well, here the lead operator has a very good view of the prime observation volume. That is what we are observing in terms of azimuth, elevation, range, and Doppler. On the right-hand side of the control panel is the seat for the skilled operator that takes care of the L-band radar, taking care of the power, what is needed for a successful observation. And on the concrete pedestal sits another and last operator that takes care of everything that has to do with imaging radar at KU band. Let me start with my presentation today. Okay, so welcome. Today I'll be talking about how can we support the orbiting operations and how can we observe them with the TIRA Space Observation Radar. A little bit of an outline. I will start with introducing a bit better the system, going into a bit more detail. Then we will discuss about how we have observed in the past certain re-entry events. I will detail on a very important function of TIRA, that is the assessment of the in-orbit status of satellites. Here, specific emphasis will be given on support of deorbiting by observing and verifying the health of the orbiting devices on board satellites. And I will finish this presentation with the exciting future that indeed lies ahead and what role can TIRA play in this changing environment. Okay, So, the tracking and imaging radar, TIRA, is located in Wachtberg near Bonn in Germany. It comprises a 34-meter Cassegrain antenna, which the whole system, as I said, weighs about 240 tons and holds a record azimuth speed of 24 degrees per second in azimuth, and the antenna can also move at a speed of 6 degrees per second in elevation. The whole system is protected by a 47.5 meter radome. TIRA actually consists of two radars. The first, the tracking radar, is operating at the L-band at a center frequency of about 1.333 gigahertz. This radar is sensitive enough to detect a 2 centimeter sphere at a range of about 1,000 kilometers. This is the radar that actually provides us with high precision orbital parameters of satellites. The second radar, the Ku-band radar, operates at a frequency of 16.7 gigahertz, and with this radar we can obtain high spatial resolution inverse synthetic aperture radar images of space objects. TIRA is a pivotal experimental facility for the development, investigation, and application of radar techniques for the detection and observation of objects in space. The radar data, as well as the in-house developed techniques, are used to determine characteristics of the objects, that is, precise orbital elements, intrinsic motion parameters, estimates of their orbital lifetime, as well as their shape and size. TIRA also provides valuable support for space missions. For example, during the launch and early operations phase, we can obtain the status assessment of already flying satellites, as well as damage analysis thereof. Now, a recent event that many people remember in the community discussing about orbital decay was Tiangong I. Tiangong I was the first experimental Chinese space station launched in 2011 that carried out a number of successful operations in orbit. Now, there was no contact with the ground since 2016, and the space station was doomed to a natural decay, which happened on the 1st of April in 2018. In this case, TIRA provided accurate tracking and intrinsic rotation data, which were very useful for the re-entry estimation, both time and, of course, spatial. We have obtained the temporal evolution of the intrinsic rotation rate, and you can see this right here in this plot. So this is the rotation rate about, a bit more than a year prior to the actual re-entry, And these continuous observations during the last phases of the re-entry gave us hints that there was a significant increase already at a height above 150 kilometers. Furthermore, we have estimated the spacecraft's cross-sectional area, where we saw also a significant decrease for about 65 square meters to about 25 square meters during the last phases of the re-entry. Here in the upper right corner, you can see two images of Tiangong I obtained with TIRA's Ku-band imaging radar, one with a model overlaid and one without. Another example, more recent this time, was a Soyuz 2.1 second stage that was launched in November 2019 and re-entered naturally on the 18th of July 2020. In this sketch up here, you can see a sketch of the full launch vehicle, and we are interested in this second stage, which was the target of our analysis. In this case, TIRA contributed with accurate orbit examination for re-entry estimates again. And indeed, down here you can see our re-entry predictions. In the y-axis is the estimated re-entry epoch, while here is the date of the prediction. And as you can see, as we go more and more closer to the point of re-entry, the errors diminish. Furthermore, here is another plot of a semi-major axis of the orbit with time. We have observations given from two line elements data, and the modeling here shown in red up to the point of final re-entry. We have also attempted, and we were successful with the in-orbit status assessment until the day of re-entry of this second stage. And we have also performed intrinsic rotation analysis, which indicate the mild rotation for the object of about 1 to 2 degrees per second. Here at the bottom right, you can see two radar images of Soyuz 2.1V obtained on 29th of June 2020, some 3 weeks prior to its re-entry. Tiangong II, and here we are changing towards the regime of controlled re-entry. Tiangong II was the second Chinese experimental space station with dimensions very comparable to Tiangong I, with a mass of about 8 tons. It was, in this case, Tiangong II was deorbited as planned in July 2019, and TIRA also here provides accurate tracking and intrinsic rotation data, which are very useful for re-entry estimates. We've done that until a few weeks prior to the planned re-entry in this case, and we assessed also the status of the space station with regards to potential external damage, for example, missing components, etc. On the right-hand side, you can see two inverse synthetic aperture radar images obtained with TIRA on the 26th of February 2019 of Tiangong II. Now, a very important function of TIRA is the assessment of the in-orbit status of satellites. Here we're going to give a bit of specific emphasis on two rocket bodies. In the first case, we have an H-2A rocket body, which is a rocket vehicle, a launch vehicle operated by the Japanese Space Agency, JAXA. This is depicted up here in the right-hand side of the slide. You can see an ISAR image obtained with TIRA, as well as a smaller sketch that can orientate you as to how the vehicle actually looks like. In this case, we have performed a status assessment and verification after we have received the notification for a potential or a possible fragmentation event in orbit. This is especially important, the assessment of in-orbit status, also for future attempts of deorbiting. An example here is the German company Orbit Recycling, which aims at capturing in geotransfer orbit, deorbiting and recycling Ariane 5 upper stages on the surface of the Moon. Just a little bit of a back-of-the-envelope calculation here. Right now there exist about or a bit more than 60 such stages in geotransfer orbit, where one has 75% of the transfer cost already paid. Each one of them carries 2.5 tons of aluminium, so one can see that this is actually a good business case for the future space economy. The TIRA contribution here is that we aim at characterizing the rotational status of Ariane 5 upper stages in geotransfer orbit, and that is especially important for mission design, for a design of this mission that aims at grabbing, deorbiting these upper stages on the Moon. We have started with an initial observation of an Ariane 4 H10 upper stage in low Earth orbit. The image is shown here. And we have also obtained promising results for 4 Ariane 5 upper stages, this time in geotransfer orbit, which is our target anyway, where we have performed observations from from ranges from about 5.5 to 6,000 kilometers up to ranges of longer than 20,000 kilometers. TIRA, however, doesn't only image. A wealth of information can be obtained by carefully analyzing the recorded radar cross-section during an observation. This temporal variation of the target's cross-section, that an example is shown here, on the y-axis, you can see plotted the radar cross-section is decibels relative to 1 square meter, and in the x-axis, the time along the observation. Now, This RCS signature, this radar cross-section signature, comes from Nabeo 1, which is a drag sail, a deorbiting device, attached to an electron rocket kick stage. The kick stage itself has a diameter of about 1.2 meters and a length of half a meter. The drag sail provides, when deployed, an area of about 2.5 meters, that is about 1.6 times 1.6 meters each side. Now, the drag sail is mounted off-center on the electron upper stage, and this results in an expected tumbling in orbit. We have performed observations with TIRA. We have obtained this, among others, this RCS signature, and yet we have indeed verified and confirmed that we see this high tumbling rate. This is characteristic, if you notice in the radar cross-section signature, from this jittery, very variable, very high variability in the RCS. And this tells us that the target is actually tumbling. When this can complicate imaging, but already from the RCS signature we can safely, or we can get a lot of information about the target. A further example, this time taking advantage of the high-resolution imaging capabilities of TIRA, is Carbonite I. Carbonite I is an SSTL testbed for Earth observation technologies, a satellite that weighs or has a mass of about 80 kilograms. It was launched in July 2015 into low Earth orbit at a height of about 650 kilometers. It carries with it the Icarus III drag sail, which provides, when deployed, a drag area, an increased drag area of about 2 square meters. The target of such devices is that they provide additional drag after the end of the mission, so that the satellite naturally decays and is destroyed after the interaction with the upper stages of the atmosphere. Now, the end of mission for this specific satellite and the sail deployment was marked on the 7th of November 2018. We have performed observations with TIRA only 2 days later, on the 9th of November 2018. We have obtained accurate tracking and imaging of the target. We have performed an assessment of the satellite status of the intrinsic rotation, where we don't see any signs of fast intrinsic rotation. And we have also managed to successfully verify that the drag sail is deployed. In the upper right corner right here, you can see an ISA image obtained with TIRA with a model of the satellite overlaid, as well as a photograph of the deployed drag sail from the laboratory. Just as an indication here, I am also plotting the semi-major axis of the orbit of the satellite in kilometers with time, where you can see the slight change of slope prior to and after the end of mission and deployment of the drag sail. This will be seen clearer in the very next case, where we have Microscope. Microscope was a CNES, the French Space Center Space Agency science mission that was launched in April 2016 into low Earth orbit at a height of about 780 kilometers. Apart from its science mission, Microscope served as a test bed for the IDEAS deorbiting system, which comprises 2 deployable 4.5 meter booms with 2 drag sails. The mass of the system is 12 kilograms and provides an increased drag area to the satellite of 6.3 square meters. It also provides compliance with the 25-year deorbiting rule after the end of service of the satellite. The end of mission and the booms were deployed. The end of mission was marked and the booms were deployed on the 16th of October 2018. And CNES has requested a status assessment and confirmation for the successful deployment of the drag booms using high-resolution imaging with TIRA. We were provided by CNES with a detailed model of the satellite, and this modeling and comparison between the model and our data has shown that indeed the deployment of the IDEA system happened successfully. Now, this comparison between model and data happened on two different levels. That is, first, the length of the booms, where we see good agreement between the model or what is expected and what we see, as well as the very characteristic 42-degree angle between the two booms. In the upper right corner here, you can see two ISAR images obtained on the 16th of October, the same day of deployment of the booms of Microscope. And here now is much more evident the regime before and after deployment of the drag booms. So this is again the semi-major axis, time, and one can clearly see here the accelerated rate of the shrinkage of for the semi-major axis. Now, an exciting future lies ahead in the field. As space debris accumulates, it becomes a real danger for space assets. That is what gives the motivation for the dawning of the active space debris removal era. That has already become almost a necessity, and there's very active research going into this field. Here, in active debris removal, there is a wide range of potential applications and collaboration at very many different levels. One example is the ESA Select Clear Space 1 mission, which aims at grabbing and deorbiting a Vespa adapter as used by the Vega European launcher. Vespa, or one of them, the target of this mission, is in low Earth orbit with an apogee of 800 and a perigee of 663 kilometers, and the mission to grab it and deorbit it is bound to launch in 2025. That is pretty soon. With TIRA, however, we started already working towards this direction. We've performed observations of Vespa in 2019 and 2020, performed detailed 3D modeling, obtained status assessment, and detailed intrinsic rotation analysis. In the upper right corner here is an ISA image of the object with a model that we have overlaid. And this helps us in obtaining this intrinsic rotation for the target. And what we have seen is that the target is intact and shows a low rotation rate of about 0.1 degrees per second. That is actually in accordance with previous findings that were based on optical light curves. The take-home message here is that TIRA, with its current and future capabilities, can deliver accurate orbit determination and assessment of the rotation status of space objects, both of which are necessary for the design and success of upcoming active debris removal missions. An exciting future lies ahead also for TIRA, however, with the TIRA Further Development Program, within which we have defined two clear targets. First, the upgrade of the tracking radar receiver with the inclusion of new capabilities through advanced digital signal processing. For example, new modes for autonomous tracking and taking advantage of adaptive waveform capabilities. And the second very important target is the complete overhaul of the imaging radar, going to higher observing frequency, thus having the potential of higher spatial resolution imaging, and also taking advantage of full polarization capabilities. With this, I would like to thank you so very much, and I'm ready for some questions.
Thank you, Vassilis, for the interesting insight in your work. I'm sorry, it's very loud here. It's because we are preparing the system for measurement after our show today. I hope you understand me. So let's go ahead. Yes, even though I have been here for a long time, I am always amazed by the powerful technology. You always have to realize that we are standing here on the ground next to the antenna, which can tell hundreds of kilometers away if an antenna has been deployed on a satellite. This is awesome. But now let's go to our questions. We have some. One moment, I'll look in the chat. Yeah, Vassilis, the first question. Can you use the imaging radar independently of the tracking radar?
Okay. So, as we said already during presentation, and also you said, Jens, TIRA actually consists of two radars, one tracking and one imaging. The thing is that the two radars have, because of physical optics and the different frequencies they're using, they have two totally different sizes of beam in the sky. The L-band radar, the tracking radar, being in the L-band, operating in the L-band, has a beam of half a degree, and the KU band, the imaging radar has some tens of times smaller image. Going back to the question, we can use the tracking radar by itself without the use of the imaging radar, but the imaging radar needs the information that it obtains from the tracking radar to successfully operate and for successfully obtaining data. Not only that, I mentioned the beam sizes because during acquisition and during an observation with the imaging radar, we have to make sure, because of the much smaller beam, that we are really on target, and that tells you what kind of precision we have with the system. Radar requires the L-band radar, but the L-band radar can operate only for tracking purposes.
Okay, thank you, Vassilis. Can you say, next question, can you say something about the status with Effelsberg, the radio telescope, with Effelsberg reception and outlook with multiple beam in Effelsberg, possible with DBF in Westerbork also?
I cannot really answer about the Westerbork telescope, but I can tell you that in the past there have been so-called co-beam experiments where TIRA was transmitting and Effelsberg, the Effelsberg radio telescope, the 100-meter radio telescope here in the Eiffel, was receiving with the aim of getting a count of the population of space debris. This has been done in the past. This is something that can happen in collaboration with Effelsberg also in the future. Possibly we need to see within the research targets of the department what has priority. But it is something that has been done, and why not? It can happen in the future too. That would be because actually the combination of the two is one of the most powerful tools in Europe when it comes to space debris, the validation of space debris models.
Thank you, Vassilis. So here on the next question, here's the next question. What is the minimum size or angular size of the largest, of the target that can be imaged with TIRA? The minimum size or angular size of the target that can be imaged with TIRA?
First of all, when it comes to the imaging radar, we talk about, just because of signal-to-noise ratio considerations, more near targets, so targets in low Earth orbit. And I will just limit myself to saying that the imaging radar, and from that can give you a hint towards the answer, the imaging radar has a resolution better than 15 or 20 centimeters. Thank you.
Next question is, my question is, does the sun and the other sources of radio noise can affect the observations in radar L and K bands?
That is a nice question. Maybe it's coming from a radio astronomer in the audience. Well, radio telescopes are much more sensitive instruments because we do not actually need this kind of sensitivity with TIRA. because targets are nearer and we transmit with high power. So when it comes to radio telescopes, this is always a possibility. However, with TIRA and being in certain bands, we do not have this problem, or let's say that this problem is not a pronounced noise source during observations. However, yes, we do avoid going too close to the sun, which is a powerful radio source as well.
Thank you, Vassilis. Which frequency did you use to estimate RCS, L or KU band?
So first of all, as I said during the presentation, the RCS signature that is very useful to us is the one coming from the L-band radar that operates at the center frequency of 1.333 gigahertz. Now, I assume that here the question has to do more with the pulse repetition frequency of the radar, TIRA being a pulse radar, and this is around 30 hertz. 30 hertz.
Yeah, here's an interesting question. How do differentiate between active space debris from an operational module? Okay,
so what is the difference between space debris and operating satellites? In the case of operating satellites, the operators on the ground do have control of their space asset. When it comes to imaging or tracking with the radar, the two do not show any difference. We see what we see when it comes to space debris. Maybe they are smaller, maybe not, because space debris populations and counts are very different when it comes to different size regimes. When it comes to the radar, the two, we get images and we get radar cross sections from both. What can happen is that if we have information from the operator of an active satellite, then this can make our lives much easier when it comes to the observation and further analysis than in the case of a non-cooperative space debris piece. Thank you. Hope I am.
Here's another special question. Which kind of space debris is apt to be recycled on the moon, and when will that be possible?
When will that be possible? I really cannot answer. Maybe within the current decade, maybe within the next decade. Let's first go to the moon in 2024 with the Artemis mission that is planned by the US in collaboration with Europe and Japan, and then we take it from there. What space debris is more possible to be recycled, however, is an example that I showed is the Ariane 5 upper stages, which with their high content when it comes to aluminum. Each contains about 2.5 tons of aluminum, and these are good targets for recycling on the moon. Keep in mind here that recycling on the moon requires also technologies that do not have to do with observation, grabbing, deorbiting the space debris, but also with technologies of recycling in situ. That means furnaces to melt the material, potentially 3D printing on the moon, and this is also technologies that have to be developed in order to reach a stage that we are ready for such a space economy and such applications. That is why I cannot really answer from my position when such a thing could be doable.
Wonderful. Thank you for your answers. That's all the questions for today. Thank you again for your participation. I hope you enjoyed it. Tomorrow morning you will get another short survey as usual. We would appreciate if you would take the 2 minutes and answer the 4 questions. On Friday you will also receive the presentation slides from today. And if you want to share the presentations with colleagues or friends, 3 weeks from today it will be published on our YouTube channel Fraunhofer FHR. Finally, let's take a look at the next presentations. We will continue in a 2-week rhythm. Next time on October 26th, there will be a German talk on 3D imaging radar technical instruction. The next English lecture will be on November 11 on the topic synthesis of radar's raw data in traffic scenarios by ray tracing. So if you haven't registered yet, do it now. We will see you again in 2 weeks. Take care and stay healthy. Goodbye.